Dr. Liz Bagshaw and Dr. Mike Pryor-Jones are going to be talking to us next. So Dr. Liz Bagshaw is a senior lecturer in the Earth and Ocean Sciences School at Cardiff University. Liz did her PhD in postdoc training at the University of Bristol, covering both biogeochemistry and aerospace engineering. She moved to Cardiff in 2014, and there she heads the Cold Climate Research Group, exploring new techniques to assess life in extreme cold climates on Earth and beyond, now and throughout history. She's interested in exploring the chemistry of microbial habitats in glacial environments, and so is currently focused on finding new methods to track water through glaciers. This has led her to explore wireless techniques for measuring water in places where microbes might like to live, for example, in the subglacial drainage systems beneath large ice sheets. So Dr. Mike Pryor-Jones is currently a postdoc researcher in the same school at Cardiff University. And his background is in electronic engineering and his career has included working for the BBC, British Antarctic Survey, SHARP, and as an engineering consultant. He's the chair of SATCOM Forum, which is an international interest group on satellite communications for field data collection within the World Meteorological Organization. And his current research is in the development of low-cost wireless field instruments for glaciology and hydrology, most notably Cryoegg, and I believe that is what we're going to be hearing about now. So if one of you can share your screen, then you can take it away.
We're good to go. Okay, thank you very much for the invitation. Thank you to the conveners for inviting us. Thank you to Jade for an excellent presentation. Enjoyed that very much. So Liz and I are going to do a double act. So I'm going to talk mostly about the instrument design and the results we've had from our field campaign in 2019, but the project has quite a long history which predates my involvement in the project, so Liz is going to start by explaining that. I'd also like to acknowledge my co-authors, our co-authors, for all of their support, and there's some more thanks on the final slide. So, but for now, Liz. Okay,
so yeah, if you could move to the next slide for me, Mike.
Sorry. Yeah.
That's all right. Some of you may have seen some of our work on wireless instrumentation before, and what we wanted to do was kind of give you a bit of a potted history of what's going on with Cryoegg in the past and what's going on with Cryoegg today. So as Christine mentioned, I'm obsessed with finding habitats underneath the ice, and I got frustrated with what was available, so I decided to start making my own sensors. We began doing this in around about 2010-ish, developing very small wireless sensors that could transit through the subglacial drainage system. These were known as e-tracers. The idea was that we would send them into the drainage system, they'd measure the water pressure in the drainage system, and then they'd pop out the front and we would seamlessly collect them from the raging glacial torrents. Obviously, this didn't work particularly well, but what we did learn from the e-tracer project, that we could transmit the data from the e-tracers through the ice using a very, very low-cost radio transmitter. So this led us on to work some more on the Cryoegg, where the idea of this project was to really characterize the wireless data transmission methods through ice. So we did a lot of work down on Lovell Glacier in southwest Greenland, looking at the radio transmission properties in temperate ice, trying to figure out which frequencies would work best, trying to figure out what sort of size of sensor we would need to get it into the drainage system. We also did a lot of work characterizing the performance of the radio transmission and the sensors themselves in proglacial lakes and in moulins to try and understand what sensors would work best. We just use very simple sensors at the moment, but we're trying to get measurements of temperature, pressure, and electrical conductivity. And those are important because with that information, we can hopefully tell a lot about the flow path of the water before it gets to the egg and as the egg transits through the drainage system. So the project kind of stalled for a little while, and then we had some more funding for it in 2018 from the UK Engineering Council. And the goal of this project was to move on from the work that we'd done in southwest Greenland in temperate ice to look at how the data could be transmitted through much deeper ice. And in some ways this is much easier because the ice is colder, so you've got less water to worry about. but in other ways it's much harder because we've got a lot more ice to deal with. We've been working with a number of different receivers, which Mike's going to introduce along with the Cryoegg technology. And the goals of the project at this stage was to figure out what works in the cold ice and what works operationally on the surface. And we were lucky enough to have a number of different deployment opportunities working with a couple of different subglacial access projects, which Mike's going to talk about now. Handing over to you, Mike.
Thank you, Liz. So yeah, I'm going to sort of attempt to mix my modes of presentation here. So if people can see me on the camera, here is Cryoegg in my hand. It's about the size of a grapefruit. It weighs about just over 1 kilo. If you look at the top right graphic on the slide, you can see that it's made in 2 halves with an upper and a lower portion. And it's made from a hard plastic, acetyl copolymer. It's very hard engineering plastic, which we have machined to the spherical shape, which makes it easy for the Cryoegg to travel underneath the glacier. So the design is that the lower half of the case contains the main part of the electronics, and the upper part, leaving the upper part clear for the antenna, which needs to be clear of any metal components. So that's why the case is plastic. What we started to do when I joined the project in 2019 was to look at what was the best available technology on the market. And in engineering, we always like to avoid reinventing the wheel if possible, and try and find some existing technology. And we were very fortunate that with a little bit of research, we found the world of smart metering from the utility sector. And the radio transmitter and the antenna that we use here both come from that sector. They would normally be used to read water meters in Paris and 1 or 2 other cities. And the radio transmitters are from a Norwegian company called Radiocrafts. The antenna is from a company in Ireland called Subglacial. And this is a standard called wireless M-bus. It comes to us more or less as a complete package, and we just put data in at one end and get data out the other, which is amazing. The important thing is that it works at 169 megahertz in the VHF band, which was quite similar to where Liz had been working before. And so as an off-the-shelf solution, it's proven to be extremely effective. And then inside Cryoegg, so this is one of the sets of circuit boards, and I'll hold that up to the camera. We have this kind of club sandwich arrangement of 3 circuit boards. The top one has the radio transmitter on it. The middle one has the processor and the battery, and the bottom one has the sensors, which, as Liz says, is electrical conductivity, temperature, and pressure. So that's the transmitting side of the system. And then the other end, of course, is that we need a receiver. And here in some pictures of the receivers. So this main picture here, top left, is the drill trench at the East Greenland Ice Core project, where Liz was doing the first field tests. And we have this large cross-Yagi antenna, which basically allows us to receive the signal from Cryoegg regardless of its orientation, which is quite important because it's spherical and it could be any way around. And it's held up on this big green plastic frame, which is actually a children's climbing frame called Quadro. We wanted something non-metallic to avoid disturbing the antenna pattern, and Quadro very kindly supplied that to us. And they were quite amused by the idea that we were going to use it for science. And then the right-hand picture shows the receiver, which is in this box here. Hooked up to Liz's laptop. And the nice thing about this, certainly compared with the previous implementation, is that we can get our data in real time, and you can literally see the data coming in on the laptop. You know if the system's working. The other side of it, we experimented with working with Liban Loke at Lancaster University and Keith Nichols at the British Antarctic Survey to use their AP-RES phase-sensitive radar. And by putting it into a special mode, we can effectively use it as a receiver and record the signal coming from Cryoegg, which means that potentially we can use that for long-term deployments in the future, because their equipment's already set up to be autonomous for a year or more, given enough battery power. So, but as yet, we can't decode from AP-RES in real time. So for the field tests, it's easier to use the other receiver. So in 2019, we were lucky to have 3 different field trials. Firstly, we went to the deep borehole at the East Greenland Ice Core project in northeast Greenland, and there they had drilled a 2-kilometre hole. In fact, we got there just as they were finishing drilling for the season, and Liz tested the Cryoegg several times up and down the borehole, and the lowest data we got, or the deepest we got data from, was just over 1.3 kilometres, and we think we had a mechanical failure because the instrument came back full of drill fluid. The mechanical design is the weakest part of it because I'm an electronic engineer and this was my first introduction to mechanical design. So we hope that with some improvement and some help from colleagues in Cardiff, we'll improve that for next time. But I thought that was pretty good for a first effort, given that our previous best record had been about 500 metres. Meanwhile, while Liz was at eScript, I was at Sirmik-Yalek, pardon my Greenlandic, otherwise known as Subglacial in West Greenland, with the responder team led by Paul Christopherson from Cambridge. And we tried a hot water drilled deployment there, which didn't go well for technical reasons. And then we also tried deploying it in a very large Mulan, which worked initially, but the Mulan turned out to be very strong and whizzed the unit off the end of the line, and it went whizzing off into the subglacial environment out of range of our receiver. So I don't have any data to present from that. I think I've got about 4 points. But we had a much more successful season later in August 2019 with Mara Verda and colleagues from ETH Zurich. We went to the Rhone Glacier in Switzerland. And Mara had drilled a 150 metre deep artificial Mulan the previous season, where he basically hot water drilled a hole and then diverted a stream into it. And we were able to make several measurements in this Mulan, lowering Cryoegg into it. And we've got a demonstration, which I'll show you a plot from in a minute, of doing salt discharge gauging, actually measuring the discharge of the Mulan in situ by pouring salt through it and observing what's going on with Cryoegg. So here are some results. Everybody loves a graph. This is the result from the East Greenland Ice Core project test. So what we have here are the results, the data from 3 sensors, and we've plotted every data packet we got that came up from Cryoegg. So you can see with the green blobs here that the pressure increases as you would expect with depth below the surface, and it kind of peters out beyond about 1,300 meters. That's where we believe the instrument was leaking. We also have the temperature from 2 different sensors. So Cryoegg actually carries 2 temperature sensors. One, a digital sensor shown here in blue, which is actually part of the pressure sensor. And we weren't sure how well this was going to work because the manufacturer's data sheet just basically didn't give any indication of how it performed below freezing. And so we built our own pressure sensor using a platinum resistance PT1000 sensor. And that's this one here shown in red. And because the 2 are not calibrated together, that's why there's some variation between them. Also, the PT1000 on this particular instrument, and we fixed this on a later design, the PT1000 is inside the case and not very well connected to the outside, so it will be a little bit warmer. And the instrument was warm before it went in the borehole, so this is definitely not a temperature profile of the eScript borehole. It's just a temperature record of the instrument being chilled down to the sort of -30 ambient temperature inside the glacier. But we have data from 1.3 kilometers below the glacier, and we got a nice continuous record in real time all the way down. So pretty pleased with that. Moving on to the next slide. This is a nice slide from our studies on the Rhone Glacier, again in the artificial Mulan that Mara had created the previous year. And what I want you to look at is the red plot here, and this sharp rise is when we're lowering Cryoegg down into the Mulan, and it goes into the water, and we're plotting the water pressure here converted to head of water equivalent. So we lower it into about 25, 26 meters of water. And at that point, we then left the data logger running and went to set up another experiment. And while it was running, we came back to it and discovered that the water pressure had dropped over the course of the next hour or so, as the Mulan is the backed up water in the Mulan has drained out. So we've actually captured that in the pressure record. There's a gap here while we unplugged the antenna briefly, and then it returned to atmospheric pressure. So all that water, all that 25 meter head of water had drained away in the course of about an hour. And what's interesting, if you look at these kind of teal colored crosses here, so these are the signal strength that's come back from the data. And you can see that in the left-hand side here, where the instrument's being lowered in, and in the right-hand side here, you've got this huge variation in signal strength, more than sort of 20 decibels. And that's basically because Cryoegg's antenna is not perfectly symmetrical, and so it's being bounced around in the waterfall inside the Mulan, and you're getting a lot of variation in signal strength because of the antenna pattern and because of the variable attenuation caused by the flowing water. Once it goes into the deep water, it all stabilizes, and then as the Mulan drains, you can see the attenuation drop off as the water attenuation reduces. So we've got a really nice kind of indication of the meltwater's effect on the radio there, as well as being able to observe sort of hydrologically what's going on. And then finally, this is the salt trace. So because Cryoegg carries this electrical conductivity instrument, by putting a slug of salty water into one of the streams that feeds into the Moulin, we can then see that salt slug pass through the bottom of the Moulin and observe how it's, the discharge of the Moulin during that time, and that's observed in situ. Normally people measure Moulins, as I understand it, by observing the water that goes into them, but in this case we could actually observe it in situ and see that in real time. So also very interesting. And really these plots, this is not science as such, this is a demonstration of the capability of the instrument. And this is kind of where I wanted to conclude, is to say that the instrument is usable as it currently stands, and we've got a few small improvements to make in the coming months. So yeah, some design enhancements we'd like to do. We'd like to improve the sealing against external pressure, very definitely. We're hoping that eScript will get to the bottom of the Northeast Greenland ice stream 2.5 kilometres down, and we'd like to put Cryoegg down there because that would be very exciting, but we need to be able to stand up to 250 bars of pressure. So we definitely need to do some mechanical improvements. We're going to add a hook attachment point just to make it easier to handle Cryoegg during the testing, whereas ultimately when it's deployed, it'll be let go on its own. And we're going to improve the transmitting antenna performance, and we're going to work with our colleagues at Tauglas on trying to improve that, just so that we definitely make sure that we can get the data from 2.5 kilometres down. Finally, we've got a partnership with a company called Tadiran, who make batteries, and their batteries have a much higher efficiency than the type we've used, so we're going to do a redesign to increase the battery life, and we hope to have at least 2 hourly data for 2 years from putting Cryoegg into the bottom of one of these ice streams. So yeah, a summary: it's a wireless sensor platform. It's suitable for both temperate and polar ice. The existing design, you could take it in the field tomorrow and use it through 1.3 kilometres of ice. That has worked well for us, and we'll make design improvements in 2020. And a paper is in preparation. But thank you for listening, and thank you to everyone who's helped supported us in the project, and especially to Liz.
All right, thank you, Mike and Liz, for that. Do we have any questions? And I can't see anything.
On my screen share, sorry.
All right. Well, I will start off with a question, slightly planted. Do you have any plans to adapt this for application in boreholes alone?
Well, funny how you say that, Christine. Yes, sorry, this is an in-joke because Christine and I have been collaborating for about 6 months. So what we're planning to do is to rebuild the instrumentation. Cryoegg is spherical for Liz's particular application, looking at the subglacial environment. And we're going to make a cylindrical version, which 2 of Christine's engineering students have already been working on, so that we can put it into a hot water drill borehole more readily, and also measure tilt and other parameters end glacially as well as subglacially. So yeah, that's work in progress.
And we're hoping that it's going to last multiple years in these boreholes. So I think at the moment, it's 5 years?
Maybe even 10. So the advantage of going to the cylindrical shape for the borehole means that we can use a physically much bigger battery, and because batteries tend to be cylindrical, it makes things a lot better. Yeah.
Okay, Emma has a question.
Hi, Mike and Liz, thanks for the talk. I was just wondering, are you individually making these at the moment, or are they like manufactured somewhere? So for each test you have to make the instrument, go test it, deploy it, or can it be produced more easily?
The manufacturing is a sort of mixed bag. So we have 2 subcontractors who made one who made the electronics and one who made the casework, and the actual assembly was done on that bench behind me. But yeah, so we built 6 in the first batch. We've lost 1. We've damaged another 1. So we still have a few left. But yeah, it would not be terribly difficult to make another batch, because the majority of the difficult work is done by a subcontractor, and all I really do is do the assembly, which takes me about half a day per unit.
Cool, thanks.
Yeah, but no, you can't buy one in eBay.
Until you set up your company on eBay.
Well, maybe one day.
I think Nana has a question first. Do you want me to read it out loud, Nana, or are you online? Okay, Nana asks, what's the scope for adding more sensors for being able to distinguish between different kinds of impurities in the basal water?
Go on, Liz.
So in fact, this is a great question, and this is the future plans for the instrument. In fact, we submitted a funding application yesterday to add some more biogeochemical sensors on board, primarily to look at water quality and habitability of sub-ice environments. So the first targets are oxygen and pH, which I would be really interested in. That's from a kind of biogeochemical perspective. And then from a glaciological perspective, Mike and Christine are already working on incorporating a tilt sensor. So yes, I mean, the challenge of the Cryoegg project so far has been doing the radio transfer and doing the kind of making a shell that works under the ice and that can be easily deployed, getting the receivers going. But once we've got that structure, then incorporating other sensors should be fine, she says, not doing the actual engineering anymore.
Yeah, no. To be fair, Liz, the way the design works is it's quite a modular platform, and we have quite a capable processor. And in fact, you know, even the mechanical design. So this board on the bottom is the sensors, so I can swap that for another one with different sensors.
Okay, thanks. I think, Adam, do you have a question?
Yeah, sorry, that was me checking whether I was muted or not still. Really cool stuff, it's a really exciting project. I was just wondering that does every cryoegg require quite an individual calibration, or do you think that its components are sufficiently reliable and that they're you know, the individual components are sufficiently you know, consistent as you buy them from manufacturers?
Ooh, that's a good question. I haven't done a massive intercomparison, I have to say, and certainly before deployment, we always pre-calibrate the EC sensor, the electrical conductivity, because that's the one that causes the most issues. And we would make sure we got recordings of that in different salinities of water to check that that's all working correctly. The pressure sensor is a Swiss-made thing from Keller. It's an industrial-grade sensor. I would be pretty happy that that's solid and very repeatable between units. The EC and the temperature sensors are both a design actually from our collaborators at University of Bristol, so there may be some drift and stability issues there, but there's no, as I say, if you wanted a more proven sensor, there's no issue to swap other sensors in and out of the design.
Okay, thanks very much. Do we have any more questions? I don't see anything else on the chat. I'll give you 5 seconds. Right, it looks like we're questioned out. We are about towards the end of the hour here. So I'd just like to take this opportunity to thank all of our speakers again. Thank you for being very flexible with, you know, the timing of this and the format, etc. And thank you everybody else for joining us.